Our next speaker in this session is Dr. Volker Buttgereit. Volker is the Managing Director of BMT Fluid Mechanics in Teddington in the UK. He was once an aeronautical engineer, but saw the light and moved over to wind engineering. And over the next 20 minutes, I'm sure he's going to share some of his latest thinking on the subject. Volker.
Thanks, Roy. Good afternoon. I want to talk to you today about some of the wind engineering challenges inherent in super tall building design. We've already this morning seen quite a few inspiring presentations about these type of structures, and not least talking about the need for structural optimization and talking about the extent to which these kind of structures are wind sensitive. I don't just want to talk to you about some of the wind engineering challenges themselves, but also talk a bit about how designers and wind engineers can come together to, in a much better way, support an optimization process, making use really of technology that exists. So this is typically what we face when we look at tall buildings. Invariably, they're very tall, high aspect ratio structures. They are unusual architectural arrangement, and certainly they're all. We tend to look at them as prototype structures in a way that really means that they sit outside applicable codes of practice, wind codes that we're dealing with today. Really not designed for and set up to deal with these kind of structures. So invariably, you're looking at structures that need detailed wind studies. In terms of understanding the effect of the architectural form. Structurally, we're definitely to the right of this graph here. We're dealing with highly sensitive structural systems, highly tuned structural systems that are complex in structural arrangements, not only based on core arrangements, but we're trying to mobilize external facades to really maximize the amount of stiffness that we can get out of these buildings. But one of the really driving features of these buildings is that we now, this shows how frequency of these structures varies with height against a number of accepted theories and engineering approximations. But we're very much over this side of the graph, which means we're dealing with buildings of very, very long period, pretty much irrespective of structural systems. They all sit in the range 10 to 15 seconds, which is quite new ground. This slide attempts to summarize some of the key wind engineering challenges that come with these type of structures. We're challenged in wind climate, understanding what winds do, extreme wind events do in very high heights can be challenging. I think over the years we've seen a number of very interesting presentations from Peter about the work that was done on the Burj Khalifa in Dubai. Foundation superstructure design, designing for strength and serviceability, really is governed by dynamic behavior of these structures. Facade design can be challenging because you're in quite high heights. Environmental design can be challenging because of the scale of the structure, and you can have quite strong downdrafts. Stack effects are important for this type of structure in a way that they are not for smaller buildings. And it's not unusual for these type of structures to have quite unusual termination at the top, which involves spires, and they can be highly dynamic structures. But really, the drive of the presentation I'm giving today is looking at foundation and superstructure design. This is a very key slide. I think there's some overlap with some of the other presentations that have happened today. Professor Tamara touched on vortex shedding. This is what it is. It's a smoke visualization of vortex shedding, and it really is much more important for super tall buildings than for smaller type buildings. Vortex shedding is really governed by this expression here and the extent to which it's important for your structure. ST is the Stroll number. It's essentially a body property. Once you fix the architectural shape of it, you fix this parameter here. So it just becomes a property of your building. N is the natural frequency, so the stiffness of the building comes into it. these are characteristic dimensions or can be affected by slenderness and use the wind speed. And really the question you're asking yourself as designer is whether you're going to have a problem with vortex shedding or not, is what's the wind speed U at which the shedding frequency, which is imposing dynamic loading on your structure, coincides with the natural frequency of the body, because then you can have strong resonance. This slide here shows the energy spectrum, essentially how much energy is in the aerodynamic forcing at different frequencies. The different color curves here show essentially different type body shapes. But in the previous presentation, we saw very nicely that normally we find, irrespective of shape, we're dealing with a range of Strual numbers somewhere between 0.1 and 0.2. They all sit there. And these two lines here show essentially structural wind speed, also your 50-year wind speed, and your serviceability wind speed. So what we know about super tall buildings is that the vortex shedding peak, which you see here, will sit somewhere in the design wind speed range for which we're designing the structure, either for serviceability or for structural loads. For base loads, this shows how base loads vary with wind direction for a very tall building. And vortex shedding usually manifests itself as a very narrow band peak like this, where over a very narrow band of wind angles, the building becomes very, very dynamic because the wind loading is shape driven. So that's good and bad news, because what it tells you is that you have a shape optimization process to go through, and it usually only applies for very few wind directions. So if you look at this curve here, what you realize is that if you can deal with this, then actually you're not in that bad a design regime. You can find the same for accelerations. In some cases you find that vortex shedding can occur over wind speed range that affects both acceleration and loads. In other cases, depending on where you are in the world, you find it affects either one or the other. So that's all very well. What can you do about it? We've just seen a presentation which discusses in quite some detail different kind of things that you do. Some of the subsequent slides here, I guess, overlap that. But because it's a shape-driven aerodynamic behavior, really, if you want to deal effectively with vortex shedding and get yourself into a much better design regime, you have to change the shape of the building. And that can either be done by working on the cross-sectional shape itself, or you can work on the overall building arrangement. And here's some examples of what you can achieve. If you're comparing to a rectangular shape, introducing things like rounded corners and recessed corners can easily, again, depending on where you are in the world and what the wind speed is that you're designing for. The blue curve here is what the rectangular shape gives. The orange curve shows you what you get when you have modified building geometry. But it's not unusual for you to be able to reduce space loads and key loading scenarios by 40–50%, doing something like that. We've seen the effect of twist and taper. Here's an example. If you have an untwisted tower with sharp corners, you get very, very narrow band vortex shedding. If you twist it, you can virtually get rid of it, and the gains you make in terms of loads are significant in that case. Often you have design arrangements where the top of the building largely fulfills architectural feature functionality. And there it can be quite effective to look at things like porosity, if the design allows. Here's an example of a building where we started off with a solid arrangement, and it had a vortex shedding problem in the loads, and we were then experimenting with different types of porosity to see whether it could affect improvement. And it's important to remember that really most of the time the global aerodynamic behavior of these type of structures is governed by what goes on over the top third of the building. So any shape changes or optimization that you might want to introduce into design should really concentrate on the top of the building, which is where most of the effects are generated. This shows how how it can affect the base load. And in this particular case, we were finding that by introducing only 25 porosity at the top, we were getting a reduction in base loads, which was there or thereabouts the equivalent of having 5% damping in the structure. The other thing that if you're early enough in design and you have the opportunity, that can be helpful is considering orientation of the building. And again, in the past we've seen interesting presentations on the Burj Khalifa to see how that building went through this sort of a process with good effect. So here's an example of a building that we were looking at where this is a cross-sectional shape where we're getting strong vortex separation points here and here that occurred for important wind angles, really where the wind speed was highest. And by changing the orientation of the tower slightly, in this case we were able to rotate it 30 degrees. We were able to reduce the vortex shedding response significantly with an according reduction in base loads. So these are some of the things that you might want to consider as you're looking to optimize your building for vortex shedding. And it really gets you to a very good starting point before you even consider structural optimization. But talking about how we design these structures now is something that's very close to my heart, and I think most wind engineers generally will argue that the earlier wind engineers and wind consultants are engaged in the process, the better. And this is particularly true for super tall buildings, and this slide tries to summarize it a bit. This is what a lot of these projects follow as a wind engineering strategy these days. So it's a tender and pre-concept, concept and scheme designs. Often you're not really working with a high level of detailed studies involving wind tunnel testing or other. It's not unusual at that stage to really be working with trying to get the most you can out of codes of practice or experience-based code design. And it's usually not until we get into the detailed design process when the designs have already progressed quite a way, both structurally and architecturally, that we start considering wind tunnel testing. And this is something that I think we need to, as a design community, start challenging because of the importance of vortex shedding, which is not very well described by engineering methods. We're carrying a huge design risk right to the final stage. So it's not until you drop your building in the wind tunnel that you actually find that peak that I was showing before, and you don't really know what it might be. Dynamic augmentations can easily be of the order 3, 4, depending on what you have. So you may find you're horrendously over-designed, or you may find that you're horrendously under-designed. Either way, it's bad news at the final design stage, because you've got a significant re-engineering process to go through. So for this type of structure, really, I do think we need to start pushing more detailed assessments up in the design process, and really you want to try and engage in what you might call building envelope optimization. And there have been a few projects where I think this is happening more and more, and the real benefit is that at an early stage you can reduce the design risk, and we saw a very good presentation this morning from Ahmed at Samsung showing the inverse proportionality between opportunity for reducing fees and timescale, and really this is where you can do the best work at an early stage in design, and you want to reduce the design risk so that when you're finalizing designs, you already have a very, very good understanding of what your vortex shedding is, what your loading scenarios are, but have also gone through a loop of optimizing your design. And this is something I think the wind engineering community as a whole is starting to drive up more and more hard. And really the technology that is being used lends itself very well to that, because most of the time at an early stage people look at wind loading and dynamic responses using force balances, either multiple balances that can be operated simultaneously if you're dealing with coupled towers, or single force balances. But the way the models are constructed, usually you have something that gives it strength and stiffness, but then you have lightweight material which can be formed and shaped and reshaped. So there are opportunities to use these models. Here's an example of a project we were recently involved in, where the approach was taken to, at a very early stage, to engage in what we're calling an interactive workshop. And so the way this happened was there was the models were built in a modular way so that they could be modified. And then they were lined up in the wind tunnel, and the designers attended the work on the wind tunnel and interacted with the process very closely. And what that meant was, and I mean, the analysis of wind tunnel data is now occurs relatively quickly. So really, a lot of the interpretation analysis can be online. But what that meant was that because we had a good interaction with the wind tunnel process, we were able to test 20 test configurations in a day. And I think that's really the way we should start thinking about using the wind tunnel at an early stage in design, because it really gives you an opportunity to test different shapes, test some of the things that we were discussing before, and at an early stage in design, start developing a route map for efficient design. I mean, this is quite an interesting way of presenting the data, which to be fair, was encouraged by Bill Baker, SOM at the time. This is looking at frequency, linear plot of frequency against square root of spectrum, and it not only shows what the vortex shedding peak is doing, but it essentially gives you a direct measure of dynamic energy generated by a building. And these different lines here are the design wind speeds, and you can see exactly as you're changing shape and changing configuration where the vortex shedding is sitting on relative to your design wind speeds, and you can see how you're affecting the response. So what you can then end up with is essentially a map like this, telling you how different types of building arrangements are going to affect your base load. It gives you an opportunity to look at the potential incentive for changing form. And if you have this at a very early stage in the design, it gives you a lot of confidence for going forward through the conceptual stages right into final stages. So I think I'm in reasonable time, Roy. I will finish up leaving you with some concluding remarks. The structural design of these buildings is entirely driven on dynamics. Any shape optimization, anything that you do, needs to consider dynamics. Mean wind loading usually is not relevant. And really, we're in the game of vortex control. Whatever we're doing to improve the performance of these buildings, we are in one way or another, as aerodynamicists at least, trying to control either the correlation of vortex shedding, the strength of vortex shedding, where it occurs, what wind angle it occurs on. But dealing with vortex shedding is everything. And different from smaller buildings, the design incentive is huge. And really, the feeling is that there's an opportunity as designers to use a different approach to wind engineering, whereby you're not looking at wind tunnel testing and detailed wind engineering works as a final verification tool in the way that you would have done in the past for smaller scale structures, because maybe for smaller scale structure, 200 meter tall building, the gains are maybe not as significant as they are for these type of structures. But really, if you start working more interactively with wind tunnels, using them as a tool, a design development tool, you can really make good progress on performance-based design and value engineering, really from an early start, saving time and ultimately cost to the project. And I think at that point I'll conclude the presentation.
Well, thank you for a very insightful talk on to what's available now in wind tunnel testing. Do we have any questions? We certainly have time for a few. Yukio, could you use the microphone?
The way to interactive way the wind tunnel test use is very good idea, and it is necessary, I think. And I agree with you. But I could not understand exactly about the terminology of the design risk, which are included in the design risk.
So you're asking?
Yes, about what do you mean or include in the design risk? You said high or low, or very low. You said depending upon the design stage. The design risk, you said. No. Design risk. You use the terminology.
You have the table.
Yes.
The right-hand column was to do with risk.
Yes.
And it was high. I think you was asking for a little bit of clarification on that.
Yeah,
What do you mean by high risk?
Okay. Sorry, Paul. Well, the design risk really sits in structural design. If you do not know how strong your vortex shedding is, does it largely affect the structural models, does it largely affect the accelerations. As a design team, you're carrying forward a reasonable amount of uncertainty to quite a final stage. I mean, for relatively simple shapes, yes, it's easy. If you have a monolithic structure, if it's triangular or rectangular, for given set of structural properties, you can have a reasonable guess at where the vortex shedding sits and what sort of responses you anticipate. But the problem with vortex shedding is that the dynamic augmentation is so huge that the design risk sits in, do I have a valid structural system? Do I have an efficient structural system? Are my foundation loads sufficiently conservative? Are they overly conservative? So that's really, and that's I think extreme because of the scale of structure and the type of structure that you wouldn't have ability underneath the building. So I think that as a community should probably still rethink how we do this. Yeah.
Charles.
Hi, Charles Clift with Curtin Wall Design and Consulting. My question is, you've done a good job at showing us how geometry affects the criteria for the wind. My question is always, where is the threshold of which the surface texture or roughness contributes significantly? You know, when I say, okay, we've got 10-inch deep fins or horizontal sunshades, when do we gain some kind of benefit from that, and when do you ignore it?
Yeah, that's a very good and very challenging question. I don't believe there's a simple formula for it. There is a point in where the facade texture, if you like, becomes less of certainly in terms of how the wind sees it, less of a generalized roughness, becomes more of a discrete feature that actually starts disturbing the wind flow per se, and you can start getting some local effects. I mean, look, generally anything that's less than say 10% of the building, the key width dimension of the building, we would tend to look at as generalized roughness and say, well, okay, that probably isn't that significant in terms of disrupting the kind of vortex shedding behavior that we would worry about. Once you start going on the other side of that, you need to case by case judge. Not least because it also interacts with the shape of the building. So having a certain type sunshade arrangement on a tower that's circular will possibly have, a given scale, will possibly have quite a different effect on the At 1 to 6 unit scale, it's pretty big. We're trying to do all these features.
I would have time for one more question. I see one over there.
When you take the design input as is given by the wind tunnel testing into the design of the building, as you said at the recommended stages, is there some kind of an basically is the evolution of the building type to reduce the vortex shedding effects algorithmic in a sense, or is it more based on the experience of a designer to be able to change the building around such that there is less vortex shedding?
Yeah, that's a reasonable question. To be honest, it's a mix of things. Obviously, as wind engineers, we try to feed as much of our experience into that sort of a shaping process as we can. And I think as an engineering community, we're building up more and more experience with these type of structures. So you would certainly hope to be bringing the experience into the process. But at the same time, you have project by project, you have very specific constraints, starting from how married is the client ultimately to a particular shape of the building. Is the architectural intent such that one way or another you're going to have to look at the sharp corner? What are the other constraints? And that really relies on very close and very immediate dialogue with ultimately the architect and the structural engineer. There are other constraints that apply to the layout of the building, and this process is going to be very, very mindful of that. Leave us wind engineers in the target free hand. You might end up with a window from that building not necessarily.
Okay, well, thank you very much, Volker, for that talk.